Okay, so I start this record. It will be much better than last time. You will see the full screen. And I started about the requirements and about CubeSat, nothing more, so nothing was lost. Okay, on the Teams, you will find slides, records, this bibliography, and some more. I will explain why. Also the tests. So when you get the test, you have a sheet with the exercises. I will upload it. I will also fix it. If I have time, I will edit with LaTeX. Are you familiar with LaTeX?
Yeah, I'm learning.
Great. And if I don't have time, I just write my handwrites. Did you find it last semester? The themes, the results, the solutions of the test and everything. Okay, what else? Also the syllabus is there, so the topics. And if you ask me some practical exercise or something like this, I also upload there in Teams. Bibliography. So there is this bibliography, very nice. It was written by someone else. The problem is that I cannot use them. Most of them are useless. Very interesting. I also teach the same course in Hungarian, and the bibliography is different. I mean, they have more English books. I also uploaded the English books there. But I will use a Hungarian book, and most of this stuff that I show you will be from a Hungarian book right now. Okay, this is about the requirements and everything. Okay, so first, some repeat. I tell you again what I told you last semester. And, well, I'm not a mathematician, but I like if something is collected. I want to talk about matrices. This is the main topic. The matrix is a table. It's a very, very useful stuff. And what is it? It's a representation of operators. What are operators? Linear vector functions. Okay? What is linear? What is vector? What is function? So let's start with it, with the very beginning. So, do you know what is set? Set is sum of things. It's actually not an axiom, but a fundamental definition. You must have a statement, a clear statement, and then with this statement you can collect things and then say that, okay, all people in this room who is more than 100 kilograms. That's quite exact. If I say all blue-eyed people in the room, that's not good because my eye is green or gray or something like this. So the Boolean logic should be used. There is another logic, it's called fuzzy logic, but it's not useful. Did I tell you about fuzzy logic? I just called woman's logic, so because there is something, it's yes, no, and perhaps, but very often you cannot say that something is true or not, like the color of the eye. Then you have a probability, and you can set up a logic, it's called fuzzy logic. But it's not topic of this, I just learned from IT students. So you have a statement, for example, the integer numbers. So from 0, 1, 2, 3. So that's a set. Or all number between 2 and 5. So that's a set. That's a fundamental stuff. Okay, what is pair? This is a set which contains two elements. That's quite simple. That's a set. I'm in a pair. However, you need ordered pairs. The ordered pair is if you have this type of set, then this is the first element, this is the second element. So the second element is in a set. So this is the ordered pair. There is another term, relation. The relation is pair of ordered pairs. So you have a relation that's for example, that's a relation. With these relations, well, that's something. Okay, the set is usually given by capital letters. Pair is pair. Okay, doesn't matter. Okay, the relation is often given in this. This is one stuff, and you can use this Venn diagram too. You don't need the comma. It's something fundamental, so it's just repeat. I'm pretty sure. Okay, so we have pairs, we have relations. Relations very often given by these arrows. Have you ever heard about injection? Injection, mathematical injection. And surreaction and reaction.
So one-to-one relation, one-on-one relation. Yeah, with the different names but the same thing.
Okay, what names do you know?
The one-to-one relation means every element for one set relate to one, only
Yes.
one element. And on-to relation means, I guess I didn't remember quite well. Each element can relate to more than one element of the second set.
Okay. Have you ever heard about this? You heard about this, and you?
I think so.
You should have, because in calculus, you are fresh. So you heard from calculus?
Yes, yeah.
Yes. Okay. So
Yeah.
the Balázs király, or who taught you the calculus last semester? Gábor. Okay. Interesting. Okay, I will know my colleagues after a while. Okay. So the injection is, we have two sets, X and Y, and it orders different elements from X to different elements to Y. But the Y could have more elements. That's the injection. That's you have no okay. Surreaction. You the so in here. What's this? So here you order something from the X set X for all elements of the Y. And then the injection and surreaction together is the B action. Then from all elements to the other elements you do a relation. This is still something in the air, and now we can do something. The function, it's constant of ordered pairs, and one element shows up only once. So if you have one element and you have a pair, and in the pair you have this x, y, 1, and there is another x, y, 2, then this x, y, 1 and x, y, 2 must be the same element. So this is the function that we know, this is the function what we use. That's one thing. The other thing, linearity. Everything is linear. For physicists, everything is linear. If something is not linear, then we make it linear. Why? Because this is what we can handle. That's why we have linear algebra and we don't have nonlinear algebra, because the nonlinearity is something horrible in differential equations, in normal equations, or everything. There are a lot of things that we can do. You study also physics, some physics. That's something. It's mechanics, or what did you study?
Mechanics mostly.
Mostly mechanics. Okay, so some heresy is coming. I mean, for mathematician. So we have a function, and now the ugly things is coming. We here t1, t2, x1, x2. So we say this is linear. Here a mathematician would attack me with an x or something like this, and say, okay, let's no vector. So, if this delta x and the delta t is small, then this is linear. We say this. We say for a lot of things. For example, okay, that's enough, I think, for physics right now. So everything is linear, otherwise we are in trouble. But what is linearity? Linearity has two conditions. You have a function, you have two elements from the values of the function. If you add the elements and apply the function, then the value will be the function applied for the first element plus the function applied for the second element. Either if you have a scalar, something that's not a vector or matrix or whatever, there are a lot of objects, then if you multiply the elements of an element with that so-called scalar, apply the function, then it's the same like scalar, and the element, and apply the function. So that's the general term of linearity. This is what we should have. I don't know. Oh, that's ugly. This is a horrible board. I don't understand why is this so bad. analysis. Okay, this is linearity. So we have linearity, we have function. Now I can say operators are linear vector-vector functions. Because there are more vector-vector functions. For example, in hydrodynamics you can find a lot of examples for this, or we can do a lot of things. Do you learn differential geometry, or
I think they do not.
I mean,
It's gonna be.
there is calculus, and most of the calculus, the derivation and the Taylor stuff, integration is for one variable. Do you learn for more variables something? No. Okay. Doesn't matter. Then it's not important. But doesn't matter. So that there are a lot of examples for nonlinear vector-vector functions, but we are dealing linear vector-vector functions. Sorry. Okay. Hungarian text in the English presentation. Okay. First of all, identical operator. This is just now it's the representation is matrix, but now this operator with boldface is the operator. So this vector-vector function. There is an identical operator. You multiply all operator with it. You will get the same. There is a null operator. You multiply the operator with it, and then you got the same stuff. Be careful, because multiplying from the right side and the left side not always the same. You will see it actually, but tomorrow, not today. I told this last, and also I told this the last semester, but I had no time to deal with it. This is very, very important. Mirror operators. Mirror operators are mirrors. So this in coordinate system, it's something mirroring, but it has a general term. You have a T operator, you apply for any A operator, and apply again, you got the same. That's the definition of mirror operator. Projector operator, you have any A operator, you multiply this projector operator, and you got the same operator. Well, as I told you, we had this linear algebra and differential geometry and everything together in 5+4 hour per week in the first semester when I studied. And one of my classmates was little bit confused and hit a fly and said, projection! Projection! Actually, the definition is good. Just after a while, we were fed up with everything. So, it gives the what is it? Rotation operator later. This later is today. At least you don't need to wait months for this. Okay, I told you operators could be multiplied both sides, and now you know this representation of operators are is the matrices. This matrix is just a table, nothing more. It could be n times m, so it could be square, it could be not square, it could be like a vector. And if you want to say something big, you say this is tensor. It's great. In the 60s, in science fictions, there were no computers, and when they want to be very scientific, they talk about tensor algebra and tensor analysis. That's tensor algebra. Okay, so this is a table. Very funny. There were the movies and Matrix Reloaded, and now Resurrection. So imagine this table reloaded, because it's a table actually, full of stuff. This is an m time n matrix. These are the number of the rows and the columns. And the set of all m time n matrix is this. It has no importance right now, but let's progress. Okay, spur. It's a very good Hungarian word. It's from German. We have a lot of words from French, from German, and also from Latin, and common words from Turkish. So it's a long time. Actually, this spur is the diagonal of the matrix. So if you have a matrix, then that's the spur. I mean the main diagonal. The other diagonal is the minor diagonal, but I think they don't use it. It has importance. The first index is the index of row, the second the index of the column. Okay, and we need the term of determinant to feel full. Okay, transpose. Transpose of a matrix is nothing more just a mirror for the spur, the main diagonal. Actually, I think you know this very well. The transpose of this is the same, but I also can write this type of matrix. Then its transpose is so this is 2 times 3, and this is a 3 times 2 matrix. This is the transpose. For the transpose, there are some interesting. Okay, it's other side. For the transpose, we have some calculations later. If you want to add 2 matrices, you just add together the elements. Be careful, you can add together, the operation is valid only for the same type of matrices. But you know this is just a repeat. M times M is the one matrix, and also the other is the same type, and the result is also n times n. If you want to multiply a matrix with a scalar, then just multiply all elements. You know this very well. I hope so. If not, then say, no, I don't know, I don't remember. But you remember. You remember, all of you. Great. Okay. Matrix operations. It's very interesting. I should the thematics, there are 4 types of matrix product. You can multiply only special matrices if the columns of the first matrix and the rows of the second matrix are the same. Otherwise, you cannot do the operation. It means for square matrix it's easy, but for example this, you can do the multiplication with this. Actually, you remember what is this? You take the first matrix, first element from the first row, then multiply the first element from the first column of the second matrix, and then take the second element from the first row, multiply with the first element of the second, from the second row of the first column, and add together. So this is, you remember how to do this multiplication. And which is important, so you can do in both ways. So, and it is not the same if you do this from one side to the from the left side or the on the right side. There are some equations because for square matrices, because otherwise you don't know what is the size of the result. So if so there is this these are the exponential equation of the matrices. So per definition, if it's a over 1, it's a, and m means a times m minus 1. It's the same like numbers. And also the a over 0, that's the identical matrix. Okay, there is this equations, it's the same like for scalars. You should know this. There is no people who use this without computer, because it's a lot of software and a lot of work to multiply two matrices. Okay, identity matrix and order, it's quite simple. There is for small one, there is larger. Repeat, you know this, so this A2, A3. Great. For all, okay, you do the multiplication from one side or the other, you will get the same. Okay, rank of the vectors, now it has no importance. Very briefly, there are a method how to determine this. You reducate the matrix, all matrix for a trapezoid form, or for a square matrix is a triangle, and the rank of the matrix is the row, the number of rows. This was the rank, and here we will not use the ranks. I just copied the slide from last year. Okay, and now something new, something interesting is coming. The application of this. Why we deal with this stuff. So, this is very small stuff. You, I guess, cannot see the numbers, but the value of the numbers are not important. It's a very special stuff. You have an image on the left side. Here. There is another image on the right side, and you want to add this image as a background of the first image. It's typical when you have Zoom, Skype. This is the blur and the background. So this is it. This is a general task. This is why we teach linear algebra and tensor algebra to IT students. For you it's different because quantum mechanics, chemistry, everything you need the linear equation, solving the system linear equations. But these matrices are very good for image processing. Okay, so let's the first image be a representation of an m times n image. This m times n are the pixels. It is grayscale because we are not masochist and we don't want to deal with the R, B, G. So what is the color code? We are RGB. No, sorry that I use the Hungarian spelling. Sometimes I use the French spelling. EFW. And it's E is E. It's an instrumental cluster. It's a space probe. Because and also I write the family names in capital letters because it's a French and French tradition. So we have this matrix. It's grayscale. The elements gives the color, the grayscale from the 0 to k range. 0 is black, k minus 1 is white, and k means transparency. It's very interesting actually, because in real life, usually this is there is no transparency. So in the grayscale, you are not programming. Can you? You programming?
I did metal. We worked on.
Actually, this is some general stuff. Did you do any image manipulation, paintbrush, GIMP, or anything?
No, perfect.
Paint?
This method, no.
No? Do you know how an image file looks like? What is inside? And you know RGB. RGB. You know RGB system. You know, it's general stuff. You know, sorry, I don't want to consider you silly or anything, but for example, I studied in Milton Friedman University, and I expected from the students some general knowledge. For example, what is Wi-Fi? What is dynamic IP? Because you do it at home, and they didn't know, so some of them knows, some knew, some of them didn't know, so I was not. I'm always careful. Okay, so usually it is just goes from 0 to the max value. It's usually 256, no, 55, yes, because it starts from 0, yes, the indexing starting. So here actually there is an extra, the 256, that's the case. The background is this B matrix, and the task is construct an operation. This is just the backslash C dot, so the original was a small circle and the larger circle. It could be, I don't know, a heart or a square or anything, so I just arbitrarily, I say, I use this sign. So we want to construct a matrix operation that copies the second image, the background of the first image. What we want, this operation should be transparency I mean this is bad. The image here, the first image, which is the n times n. Its background is transparent. The b n times n is the second image. Sorry, it's something malfunction. Now we want to construct that it means it's the original image, except if it is in the background. It's when it's transparent. This AIG is key, means the transparency, the background of the A image. We use this function. This function is the round to the lower integer value. Okay, this is the task. Then the solution. If we have A in this interval, then if we do this operation, just divide A with K, then its value is between 0 and 1. If I apply this function, this round function, then this A divide key is 0 or 1. That's great. This is what we want. Okay? Or with other words, if the pixel is transparent, then this value, this round A divided key is 1. So let's reverse it. 1 minus A per key is 0 if we are in the background when the A value is transparent. So the desired operation is in this form. I don't know, circle B is A per key times B plus 1 minus A per key times A. This is the desired operation. And in the picture, the solution of the image is much better than this one, but there is a matrix that's 32 times 26. And then you can see the original image, and then the background and the result. Do you understand this? Are you sure? Okay. So this is operation. It's great, and this is a matrix operation. This is one example. What you can do with it, but there are more. Some physics. Again, the typical stuff is the moment of inertia. Do you know what is moment of inertia? You know? You know? You know? Okay, you know. This is a very weird stuff. Very weird, not stuff. Very weird something, object. Because it's not enough large. What is something large? If you want to start rotating this, then it's more difficult when you do this or you do this. So this is something which the input is a vector, the output seems to be a vector, and it's different vector, so it's not scalar. There is no other way. That's a tensor, that's an operator. And this is a very, very simple stuff because there are much more about this. How you give the matrix, the tensor, inertial tensor. All elements is given with that formula, and this formula is actually very simple. It's nothing more than the distance from the axis to the actual point, and the m key is the piece or that part of the object, that's the mass of that part of the object, and the r is the vector from the axis, the actual axis, to that point that you measure. I will not do anything with this right now. This is just now theory. Perhaps tomorrow I will do something. It depends how much coffee I will take during the night. And now see, this is application of the connector data. So now you see it's something different than last semester. Okay, and now the other very important thing that I tried to explain you last time, transformations. This is the best in matrix. Actually, why do you use them? Because we are lazy. You can do this transformation with coordinate system and everything, but if you put everything in tables and you have standard operation, standard algorithms, standard procedures to use it, then you can spare time. I talked about the SPICE kernel by NASA, which is for which determines the location and orientation of a camera on a special spacecraft, for example, the Jovian system or someone else. This is much more simple. First rotation, this is rotation in a plane, in 2D. You have an alpha angle, and then you can rotate something, and I just take the sponge. Oh, I have many sponges. I think I will not use this board if not necessary, because on the pictures it's not so nice, and also the chalk is broken, and then I don't need manicure for a wire. Okay, so very simple. Okay. Very simple. But it could be not only 90, it could be 45, could be 30, anything. Then you don't need to meditate, just use the numbers. In 3D, it's more difficult. The rotational matrices are the following. Respectively, I don't know why I wrote it this way. The first is rotation around z-axis. Can you imagine the 3D dimension? Then rotation around the x and the y-axis. Okay. Oh, no. So you can see in 3 dimension we have an x-oriented vector. I apply this rotational matrix and I get a y-oriented vector in 3D. That's easy. You have seen this? Others?
I don't remember. What did you do to get the final? You multiplied the.
I multiplied.
Okay.
So it's 0 times 1 plus minus 1 times 0 plus 0 times 0 then 0. Then it's,
Yes, I think
you remember. Okay. Okay. This was the rotational transformation. Actually, they have deduction and everything, just I didn't write it. Mirror. You have a you have this line, and this operation is a mirror of all vectors in this plan for this line. Just mirror. Okay? I will write this in particularly tomorrow, or not, we will see. This is the vectors of the 3-dimensional space for the plan that has a normal vector n. Do you know what is the equation of a plan in a given point with a given normal vector? You remember this?
We have notes on it. We can. I don't remember.
No problem. Please remind me tomorrow, okay? And we will do some example, okay? You have a point. You have a normal. And then normal university, I'm in a rich university, a real rich university, I would say drop this goddamn board, and tomorrow I would have other board, and the same with my notebook. We don't know, but I have a problem with the keyboard, and I still have no time to take the new one. I got a new one, just I need time to install and set up the Linux, because I use Linux mostly. Okay, projection. It's also very good, projection. Projection is you have an A operator, you multiply with this projective operator, and that's very weird. This P should be T or something like this. It was, I will modify this stuff. Was it P? No, it was nothing. That should be T, but it was written P, but it's disturbing. So imagine the first operator is T, because it's a mirror. Oh, you're not Hungarians. Mirror tükrözés is T in Hungarian. Just you cannot pronounce it, so it should be M in an English class, not T. Sorry, sorry.
T represents the transpose, right?
Wait. Sorry. Now, here the T is transpose, but I'm perfectly confused because I learned this in Hungarian, and here at the here I just gave some examples for operators. No, the T is transpose, but here this T should be M, like mirror. I will change this. Sorry. So the languages are mixed in my my stuff, my head. Blah 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 blah. Okay, so this is projection for line which has a directional vector. Line given by a point and by a directional vector equation. You know. Okay, you know. Okay, because the others I taught you. I don't know you, and I don't know what you know. Yeah. Okay. Perpendicular projection, the plan with a normal vector. This will be given in particular tomorrow. Okay. Almost last slide, because we are out of the time. You can do shift, linear shift, linear transformation, parallel shift or parallel transformation. If you have an AB vector in 2D, then you multiply it with this matrix, and actually the third component is 0, and you will get the shift. And also in 3D, you can do as ABC should be actually. You can find the parallel transformation, the shift in 3D. So everything is possible with matrices, almost everything. If not, then there's something. There are a lot of other things about matrices, but it's too much for one class. Diagonal matrices, permutation matrices, and so-called snakes. You have seen triangular matrices, and it's important to know what is symmetric and skew-symmetric matrices. But this will be with examples tomorrow. So thank you very much. Did you consider this useful?
Of course.
Okay.
Good revision from the previous classes. I mean, it was all the revision from the previous classes.
Yes. But we will stop revision. I stop the recording.